Hello there, this is Mr. Miller, and I hope you are my geometry students. This is video number 17, and we're going to talk about distance problems. This unit is on word problems, and word problems are always kind of tough. You just have to keep trying and persist, and you'll catch it. All right, you'll get it. So there are three types of distance problems we're going to talk about. The first kind are when people are moving in opposite directions. They could be in cars or bikes or jogging or in trains or in airplanes. It doesn't really matter. There's moving in directly opposite directions. The second type of problem is people moving toward each other. And the last type of problem is one person chasing another person. They're going in the same direction, but maybe one started later or one's going faster. All right, we have three examples, one of each type of distance problem. And if you follow along, hopefully this will help you in class. Here's example one. Two motorcycles start at the same location and travel in opposite directions. So here they are. First guy is kind of going towards the left, and the second one's going towards the right. One motorcycle is going 35 miles per hour, so I'll make this guy the 35 mph, miles per hour, and the other one is going 50 miles per hour. So that dog there is going 50 miles per hour. Okay, now it says how long will it take them to be 204 miles apart? So we're going to start with a guess. And the reason why we kind of start with a guess is if we're not sure how to write an equation, it may help us understand how to set up the problem. So suppose it takes 1.5 hours. The first guy going to the left, after 1.5 hours, he travels 35 times 1.5 miles. It's how fast he's going, miles per hour, times how long he travels. Then the second person, we're going to add to it because their total distance has to be 204. So the second person is traveling at 50 miles per hour, and after 1.5 hours, they've traveled 50 times 1.5. Now, that's just our guess, and if it's 204, we're done. Okay, so let me figure out how far they've gone together. So 35 times 1.5 plus 50 times 1.5 equals 127.5 miles. Well, we were shooting for 204 miles, so it's going to take them longer. The key in this problem is to realize that we're adding the distances. It's their total distance. One goes in one direction, one goes in the other, and we're looking for their combined distance to be 204 miles. Now, in this equation, we can replace our guess with the variable t for time. It occurred twice, in the first term and the second term. So when we do that, we're going to get a really easy equation to solve. 35t plus 50t equals, we're going to set it to what we want the distance to be, 204. So the first term is how far the first motorcycle goes. Second term is how far the second motorcycle goes. If we combine like terms, we get 85t equals 204. This is really easy to solve. We just got to do a division. So 204 divided by 85 ends up being 2.4 hours. That's 0.4 hours is a little bit less than half an hour, so a little bit less than 2.5 hours. So remember, this doesn't mean 2 hours and 40 minutes. It's 2 hours and 4/10 of an hour, 2.4 hours. Like I said, a little bit less than 2.5. All right, that's our first example. Second example is going to end up being very similar. Even though they're traveling towards each other, the fact is still the same. Their combined distance is what we're after. So this guy's traveling to the right, and this one's traveling to the left. Okay, it says two bicycles are initially 36 miles apart. So they're originally 36 miles that way. The first bike is going 8 miles per hour, and the second bike is going 12. So 8 miles per hour, and this guy 12 miles per hour. All right, how long will it take for them to meet? Well, the secret here is that when they meet, wherever it is in this 36 miles, their total distance is 36. So however far the first guy has traveled, The other bicycler has traveled the rest of the way in order for them to meet. So this looks a lot like the last problem. The first bike traveled 8 miles per hour times, we're guessing 2.5 hours, plus the distance the second one traveled is, or his speed is 12, times how fast he went, and together this is how far they both traveled. And we want to know, is this equal to 36? Okay, let's check it out. It ends up equaling 50. So that's too much. This can't quite be right. So it's not 2.5. But just like the last problem, let's look where we put our time. We put it in two places. The time occurred there in the first term and here in the second term. So if we write our equation in terms of t, the first bicyclist travels 8 times t, the second bicyclist travels 12 times t, and we want their total distance to be 36. Okay, so if we combine like terms, 20t equals 36, then we have to divide by 20. Now I get 1.8 hours. Okay, so at 1.8 hours, they're going to meet. When they meet, together they've traveled 36 miles. All right, let's take a look at the last example. The last example is someone chasing someone. This one's a little bit more advanced. We can do it though. It says Janet starts jogging down the trail at 4.5 miles per hour for a half an hour. So she gets a head start. And when Bob gets there, he starts running at 6 miles per hour after her. So how long will Janet have been running when Bob catches up to her? So Bob's going 6 miles per hour in the same direction. 6 miles per hour, but he's been running for a half an hour less. And Janet is going 4.5 miles per hour. Seems like he's going to catch her eventually. He's going faster. All right, will it take 1.5 hours? Now, here's the key. So they both start at the same place, and when they meet each other, they've gone the same distance. All right, so we have to set their distances equal to each other. So Janet's distance is 4.5 times 1.5. That's Janet's distance. And we want to know, does that equal the distance Bob has ran? Because like I say, when they pass each other, they're on the same point of the track or the trail. Okay, so Bob's distance is 6. And we're going to multiply it by not 1.5, but 1.0, because he's been traveling a half hour less. Okay, on the left, we see Janet's distance is 6.75 miles. Wow, she's ran a long ways. And after an hour and a half after she's been running, he will have run 6 miles. These aren't quite the same. Okay, so it's not quite right. After 1.5 hours, they haven't gone the same distance. Again, she's been running for 1.5 hours. He's been running for a half hour less. Okay, let's set up an equation. We're going to let t be Janet's time. So she's been running 4.5 times t. That's her distance. And we want to know when Bob's ran the same distance. So his speed times his time. But we got to put t minus 0.5 because he's been traveling half hour less. All right, that's the tricky part. That's why this is an advanced problem. The distances have to be equal, and he's been traveling a little bit less time. So we have to distribute 4.5t equals 6t minus 3. Then if I subtract 6t from both sides, I get minus 1.5t equals negative 3. And if you divide, you get t equals 2. So after 2 hours of Janet running, Bob catches up with her. They've traveled the same distance. It's time for the journal assignment. So don't panic. These aren't the challenge problems. These problems are like the first 2 examples. So this first problem, number 1, 2 trains going in opposite directions. it's like example 1. And this one, two runners running toward each other, this is like example 2. Okay, so go back, look at the examples 1 and 2, and see if you can explain the guess, whether it's right or wrong, and write an equation and solve it. Okay, give it a try. You'll be ready for class. Take care.